We discussed page table. So page table has translation information. So for each virtual page, it has an entry in the page table. So if the page has been moved into physical memory, then it has physical page number for that virtual page. Okay? So using this virtual page, you can do the translation. Okay? So operating system maintains this page table for each process, for each loading program. So essentially, the processor generates virtual address. So it can be instruction address or data address. But to access physical memory, you don't know where this address is in the physical memory because those are two different addresses. So you need a translation before you access main memory. So to do the translation, you have to look up the page table. The page table is a kernel data structure that's maintained by the operating system kernel. So if you, for every memory reference, if you ask operating system to do the translation, it takes too much time. Right? So we need some acceleration. And it's supported by this hardware called translation look aside buffer. This is exactly a cache of page table. So initially, like every other cache, this is empty. But once you reference particular virtual page, that virtual page, that page table entry is copied into this translation look aside buffer. So next time you reference the same page, you don't have to ask the operating system. You can do the translation by looking up this hardware, looking up this table. Okay? And this translation look aside buffer, another name for TLB is MMU, Memory Management Unit. So sometimes you see a literature or paper or description of the processor, it says it has some MMU, which means it supports this virtual to physical address translation, which means the CPU supports virtual memory. Without hardware support from CPU, you cannot support virtual memory because it takes too much time. So most processors include this TLB in its internal structure, but some small embedded processors may not have this TLB, which means they cannot support virtual memory. They only support physical memory. So some embedded systems, some small systems, they don't support virtual memory. But for most of the computer systems, they support virtual memory. That means they should use the CPU that has this TLB, cache or page table entry. So if you find page table entry from TLB, it's called TLB hit, then you can do the translation right away. Because using the virtual page number, you can search this table. If you have a match, then the matching entry will provide you physical page number. Okay? And then you can concatenate this physical page number with the page offset. That becomes the physical address. Then you can access the main memory or the cache. Cache is part of the main memory. Okay? If you miss TLB, which means this page has never been moved into physical memory, then it generates TLB miss. TLB miss is an exception, which means some exceptional situation, which we have not studied in detail. But exception means the CPU can no longer continue the execution of this program. And CPU actually suspend this process. Suspend means stop the process and ask for help for the operating system. And operating system, so from the user mode, you are running the user program, and then it goes into the kernel. It goes into the kernel, the operating system actually handle this TLB miss, which means it actually look up the page table for that process and find out the page table entry and get the entry and move it into this TLB. And then it can resume the process. So after you resume, if you execute the same instruction that codes this TLB miss, it will not generate TLB miss again because you have this entry in the TLB. So it will be a TLB hit and you can continue because you can do the translation. Okay? So this is a TLB miss. So on the miss operating system, search the page table and find the missing entry and copy this entry into the TLB and then you can resume the process. Okay? And then you can continue. So TLB usually contains about 100 entries. So it can be 64 entry or 128 entry because the computer likes 2 to the power of n, right? And TLB miss compared to cache miss. Okay, 이즈램 NT에. Okay. So, like a cache on a miss, you have to pay miss penalty, which will take longer compared if you have TLB miss or cache miss. How do you think? How about the miss penalty of this TLB miss? TLB miss will take longer because you don't know? Okay. 옆에. 네. Which one? This TLB miss takes longer actually. So he's right. But why? 이 뒷줄에 오니까 이 학생들을 처음 보는 것 같으네. 가끔 뒤에 와봐야 되겠네. Any idea? You have to think. So cache miss, for example, if you do a cache miss, the hardware cache generate a miss request, right? And then the request go to the second level cache, go to the bus, chipset, and go to memory. And memory, as we have studied, it actually do a return to the data, right? You do a row access and column access. You do a burst mode DRAM access. And every cycle, using a 64-bit bus, it can transmit 8-byte data. If the cache block is 32 byte, you have to do 4-cycle bus transaction, right? Bus data transmission, and then it can come back. And it usually take, in current high-performance processor, it may take maybe a few hundred cycle, 400 or 500 cycle, okay? Because there can be a competition against, there might be other requests, and you have to wait sometimes. How about TLB miss? How long will it take? 그 옆에. Do you know what is TLB miss? You know what is page table entry? Page table. Did you come to my class in the previous lecture? Did you? 늦게 왔어? How about you? How do you think? Your face looks familiar, which means this is your first class or second class? For me, I mean, my class. First class, okay. Rabin, how do you think?
What was the last question? Because
TLB miss versus cache miss. TLB miss takes longer, and I'm asking why.
you have to look up twice.
What do you mean by twice?
For the you know, for the page of the TLB and then for the page.
You just want to find out the entry, page table entry. You don't want to find out the actual page. So I'm asking this TLB miss only, page table entry miss. Any idea?
TLB miss always means, usually means cache miss.
TLB miss always means a cache miss?
Not always, usually.
Not usually.
So, both is
That might not be the reason. There are more fundamental reasons. TLB miss takes much longer than cache miss.
Because TLB miss is to look up to the secondary memory, disk memory.
It may look up the disk or may not. You don't know.
Does it lower level of
No, cache miss also may look up the secondary memory also, right? If you do cache miss, it can be a page miss, and then you go to. So that's not the fundamental reason. Any other reason?
it has lower entry?
No. 5 bonus points. This is a simple question.
TLB is check the first check the page table list and check second check the cache miss.
No, you are missing the point. Any other answer? Okay.
We always check the TLB, so every time you look up for data, always some instructions must be done for each data.
No.
Maybe on TLB miss, you have to look up the page table entry and then you look up the memory. So there's 2 steps.
I think it's another student answered the same question, the same answer. Okay, with the same answer. That's not the reason. Okay, the point is for cache miss is handled by the hardware. You go to memory and you come back. Okay, but on a TLB miss, it's usually handled by software. It's an exception. You go to the operating system kernel, which means the current process has to be stopped, suspended, which actually require the exception handler must save the program counter and register for this process first. And then it actually invokes the operating system. And it's handled by software means it's actually running actually to be specific, it's not going into the operating system directly. The exception handler is actually part of the firmware. These firmware, these are software. These firmware are written by the CPU designers, not by the Microsoft people. Okay? So when I work on Itanium, I said we have 600 people. Some of them are these firmware engineers. They write all these exception and interrupt handlers. And this firmware is called processor abstraction layer, system abstraction layer. They actually, what they are doing is they save the state for that process, and then they try to find out the API for this event. So if current system is running Windows 64, it's running Windows 64 API. If it's running Linux, it should call Linux API that handles this TLB miss. So it eventually calls this operating system code that handles the TLB miss. What they are doing is they are looking up this page table. Page table might be in the physical memory already, or it might be in the disk drive. Find out the page table entry, and copy that entry and insert into the TLB. Usually TLB is made by the instruction. You can insert or delete the page table entry into the TLB. And all of these are learning instructions because it's software, which means there can be load or store, which means there can be many cache misses also, okay, because it's run by the software. So it has much more overhead because it's processed by the software instructions, which involve lots of memory operation also, and also it involves context save and restore, because whenever you suspend the process, you have to save the state. What instruction you have to execute next to come back, and the registered, because the exception handler and operating system code may modify the registered. So you have to save some registered as well, and you have to restore. Okay, so it's much more overhead. So the miss penalty may be a few hundred cycles. This miss penalty might be few thousand cycles or more. Okay, maybe 1,000 cycles or more, or whatever. So since miss penalty is big, and if you miss, the penalty is substantial, which means it's performance critical, right? TLB miss is more important because, as one student mentioned, every instruction they have to reference TLB because they have to look up the instruction TLB, right? For a fetch stage. And if it's a load instruction, it generates another data TLB miss, which means TLB is accessed more frequently than cache. So it's more performance critical, which means even if you pay more overhead in terms of area, sometimes it's better to implement with higher performance cache design, which is fully associative cache. Right? It gives you higher hit rate, it's faster. So you can see sometimes fully associative cache, or maybe 4A or 8A associative cache to increase hit rate and to give higher performance. Okay? And same as the cache, it's also multi-level TLB. So you have instruction TLB at the first level, data TLB, and it's backed up by second level TLB, which can contain both instruction or page table entries. Okay? It's similar to cache design. So you can have multi-level TLB, first level, second level, or third level also. For the first level TLB, it's usually separated, instruction TLB and data TLB. Same as cache. Cache usually, first level cache is separated, instruction cache and data cache, because the reference pattern and locality is a little different for instruction reference and data reference. So by separating, you can optimize the structure more optimal for that reference string. Okay? So on a miss, exception handler is invoked, and exception handler eventually calls the operating system, and this OS code search the page table and find out the missing TLB entry and insert this entry into the TLB, and then it can go back and resume. So when you execute the same instruction, it does not generate TLB miss because TLB entry has moved into the TLB by the exception handler. Okay? So TLB, since it's managed by the software, there is a hardware instruction, machine instruction called TLB insert or delete instruction. Because on a miss, you want to insert entry or you can delete. TLB miss handler, usually about 100 instructions, something like that. And so every time you do a TLB miss, it has some overhead. To accelerate this, sometimes they can implement hardware page worker. Instead of doing processing by the software, you can do it by the hardware also. And the idea is simple, but I'm not going into the detail. You can do it by hardware. So if you do hardware page worker can do the translation easily and find out the page table entry is in the main memory or not with a single memory reference. If you cannot find, then it actually generates exception. So there are multiple steps before you go into the operating system code. Okay? Okay. So there are multiple different virtual memory faults. So if the page table entry is not in TLB, this is called TLB miss. Sometimes on a TLB miss, you try to find this page table entry in main memory, right? But it may not be in main memory. It's called PTE miss. Essentially, you have to go to the secondary storage to find out the page table entry, which means the page table page that has not been moved into main memory yet. Okay? And page miss means this is for the translation, and this is actually the actual instruction when data page is not in main memory. Okay? So you look up TLB. If you miss TLB, it means TLB miss. You find TLB entry. So even if you hit the TLB, sometimes page table entry says it's not present. It means page miss. Okay? Okay? That's possible. Okay? And you look up this page TLB, and it says you can do the translation, but access violation means the page table entry has some page attribute. It says this is read-only page. And if you're trying to do a store, it means you're doing access violation. Read-only page, you're doing a write, which is not permitted. So it's prohibited. You do an access violation, and the process has to be terminated because it's doing some illegal operation. Privilege violation, some user code is trying to look up the page table, maybe to manipulate the page table, which is not permitted, right? Page table must be managed by the kernel only. So each page has some privilege level. So if you are learning the user mode and you are learning the kernel data structure, it generates privilege violation because you are trying to access kernel data structure. Okay? So all these virtual memory faults will be generated when you access TLB, because TLB has this page table entry, has all this information. Okay? Okay, this is an old system called DEC Station 3100. So this is a workstation from Digital Equipment Corporation, which was the mini computer company. Now it becomes the part of HP, I guess, because DEC was acquired by Compaq, and Compaq was acquired by HP. Okay, and this is an old system, but you can see their translation mechanism for TLB and cache. So this system uses 32-bit virtual address, which means, 효정? What does this mean, 32-bit virtual address? That means the size of virtual address determines what? No idea? The size of virtual address determines program size, right? Because each of these virtual address space is program space, right? So which means this machine, the maximum program size 4 GB, okay? And physical address is also 16 plus 14 plus 2, 32 bits. This means, Oksana?
Yeah.
Physical address is also 32 bits, right? What does this mean?
There are 2 to the power 32 addresses, different addresses.
Address is for what? Is it for physical address means?
Oh, pages. Same number of pages.
No. Page?
No?
Physical address means physical memory, DRAM.
Oh, sorry.
It means this system, the maximum main memory is 4 GB, right? What is your name? 함성욱. Okay, 성욱. Okay. So what is the page size for this system? Zero to 11. This is 12 bit, 4 kilobyte, right? 4 kilobyte. And what is this? This is TLB actually. In terms of cache organization, is this fully associative or associative or direct mapped? This one, TLB. 성호. Fully associative because it has this comparator for every entry. Okay? So it means this is fully associative TLB. Okay? And virtual page number is actually the tag. Using the virtual page number, you search this TLB entry in parallel. If you have a match, if it's valid, then it means it's a TLB hit. And actual data is the physical page number. And it should have valid bit is here. It should have presence bit and readable, writable, executable, and privilege and so on, page attributes also. But it's not shown there, shown here. But physical page number, using the physical page number, you can construct physical address, right? And physical address, the page offset should be the same because page offset is a relative position in the page. That should be the same. So it generates 32-bit physical address. Okay. 오케이. 누구한테? 자네 이름 뭔가? 광현. What is the cache size? Can you figure it out? What should be the cache size? Okay, let me ask you a simple question. How about the cache organization? Is this fully associative or direct mapped or set associative? Direct mapped. That's right, because there is only one comparator. This is direct mapped cache. Okay, 옆에. What is the block size for this cache? Block size. Here, data. 32-bit, which means 4 byte, right? Okay, and that's too simple. How many blocks in this cache? He said it's direct mapped cache, okay? And 4 byte blocks, right? And how many blocks are in this cache? You can figure it out also. How many blocks? How many blocks? 효정 옆에 자네 이름 뭔가? 병찬. 병찬, how many blocks? 2 to the power of 16?
No,
14, right. Index says 14 bit, right? And this is direct mapped. So each set has only one block, and you have how many set? 2 to the power of 14, which is 16K, right? 16K sets, and each set has one block is 4 byte. So 64 kilobyte direct mapped cache. Okay? 64 kilobyte direct mapped cache with 4 byte blocks. Okay? So from the physical address using the index, you identify the block, right? So you have decoder here, you select this block, and so this goes into the word lines, right? Word lines. And then you fetch this 32-bit 4-byte blocks. So you have 4 bytes. So using the block offset, byte offset, you select 1 byte. Okay, that is the starting byte. And then if you are asking 32 bytes, this is 32-bit processor. If you ask 32-bit data, you actually send entire block, 4 byte, to the processor. Okay? 알겠죠? Okay. Okay. So one problem for this architecture is if you want to access cache, you have to go through TLB because you have to, after the TLB translation, you generate physical address. Using the physical address, you access the cache. So assuming TLB access takes 1 cycle and cache access one cycle, then every cache access takes 2 cycles. Right? You want to accelerate this process. Okay? Sometimes going through TLB is too slow. And you can do it in parallel. You can access TLB and cache in parallel somehow. Any idea? So I'll give you 5 bonus points. Can you accelerate this process? For this architecture, we cannot accelerate, but in general, we can accelerate. Can you give any idea?
Work on virtual address and physical address, we can do both works at the same time, and if the TLB is not correct, we can then now see the physical address side works.
Right, but to access the cache, you have to extract the index. But index should be extracted from the physical address. Can you solve? Right, to access cache access, since you study cache organization, what you do is you have to do an index decoding. Right? You have to extract the index, but index should be extracted from the physical address, right? Can you? So you then, which means you need some translation.
Then translation parts can be added.
Right, so you do the translation, then you extract the index, then it will take 2 cycles, right? So can you do it better? So in this organization, we cannot do better, but if we modify something a little bit, then we can accelerate.
Maybe you can put cache index in the TLB instead of this operation.
Cache index into the TLB, what do you mean by cache index into TLB?
I don't know how to explain.
Any other idea?
The page offset of virtual address may be used as a cache index.
How?
You can just connect the page offset to the cache.
Right, but page offset are the same, but the index here, you require some virtual portion. So what can you do? At least you got 5 bonus points. If you narrow down, then I'll give you 10 bonus points. So 10 more seconds, think about it.
Can you bypass the 5 offset?
No, I'm giving him a chance. Think more.
It's kind of like bypass in the pipeline.
Bypass in the pipeline.
I mean,
Okay, you receive 5 bonus points. Send the email to TA and CC to be. You have an answer? Okay, I'll give him another. Give her another chance. Okay.
If we use the page offset, 12 bits of page offset to the cache index, the lower 12 bits,
Uh-huh.
we have 2 bits left.
Mhm.
So we will the cache to 4-way. Instead of 4-way associative.
4-way associative. In this case, 4-way associative is not enough, right? Because you need how many bits? So this is 16, this is 12, you need 4 bits.
Then 16-way.
Right, 16. So you get another 5 bonus points. 5 bonus points and 5 bonus points, okay? Okay, there are two options. So he has a point. So if you look at this page offset, virtual address page offset, physical page address page offset. This is same as physical address, this portion. So somehow if you can extract index from the virtual address page offset, you can start decoding in parallel with TLB search. Okay? But the problem here is cache index is actually larger than this page offset. So if the cache index can be extracted from here, then you can do that decoding in parallel with TLB access. So the idea is if you increase the page size this much, which means 16-bit maybe, 16-bit means 2 to the power of 64 kilobyte, then you can extract index right away from the virtual address. That's one option. You increase the page size. The other option is, as she mentioned, she mentioned, this is direct mapped cache. So index is this big, but if you make it 2-way associative, you can reduce 1 bit, right? 4-way associative, reduce 1 bit, and so on. So if you make it 16-way associative, then you need this much index, and this becomes the tag, right? Then you can extract the tag right away. Okay? That's done in the actual system. So if you look at Pentium 4 or i7, they all use this kind of technique for the first level cache access. You extract cache index here, you do the decoding, at the same time you access the TLB. So after you finish the decoding, you get the physical page number using the tag. You can search the tag compare in parallel. Then somehow you can overlap the TLB access and cache access directly, and this is called virtually indexed, physically addressed cache, because index you got from virtual address, but the tag is from the physical address. Okay? So this is virtually indexed, physically tagged cache. It's common scheme to bypass. So it had somehow bypass meaning, but so use roll bits, because roll bits of virtual address is same as physical address. So access that on cache. So if you have 8 kilobyte page, you can use row 13 bits. This is physical address, same as in physical address. So access 8 kilobyte direct mapped cache, or 16 kilobyte 2-way associative cache, or 32 kilobyte 4-way associative cache. Okay, and you can access TLB and Aaron in parallel using the virtual address and do tag compare after fetching the physical page number from the TLB. Okay, so we see actual real example from Pentium Pro in the next slide. Okay, let's review. 성우. Among 3 cache organizations, which one is the fastest? Fully associative, direct mapped, or associative? Which one is the fastest? Fully. Okay, 딩동댕. 그 다음, 아까 효정, 뭐라고 했지? 이 친구 이름이? 병찬. I'm not good at memorizing names. I can recognize face, but I don't remember name. 성욱, 병찬. Which one is the slowest among three cash organizations? Fully, direct method, or associative? Slowest. Associative, because it requires index decoding, tag compare, and then waymoffs. Okay? 자네. Which one is the largest among three cash organizations? You have same 16 kilobyte, fully, associative, or direct method cache. In terms of area, which one is the largest? 자네, 옆에. 응? associated 자네. Which one is the largest? Direct method 자네. Fully. Why? Because he answered the other two? Or do you have any reason? 몰라? Fully associative. Comparator?
All of
Yeah, that's right. It requires comparator for each entry, right? Each block. That's why fully associative cache is bigger. It's bigger, but it's faster. And it gives you higher hit rate. Which one is the smallest among three cache organizations? Minuk? Direct method. Because
just need one comparator.
one comparator and one decoder. Okay? What will happen in terms of cache TLB page miss right after context switching? 그 뒤에. Context switching means sometimes you run this process, Internet Explorer, and after the time slice, you switch to another PowerPoint, right? Then what will happen? 그 옆에. 이 친구들도 처음 보는 것 같으네. 이 친구 본 것 같고, 이 친구 처음 보는 것 같아. 그 옆에. 응? No idea? 자, 어떻게 생각해? 응? How do you see? No idea? How about you? No idea? 다 노으로 대답할 것 같은데. What will happen? So you first, the program counter is loaded with the start address of the program, okay? Because each executable there is a start symbol that contains the first, the address of the first instruction. So you try to fetch that instruction, right? So what will you do? You access TLB first, right? You do the translation. You generate TLB miss, right? Because instruction TLB, the page table entry is not there, right? And then the operating system is invoked. It tries to find out the page table entry for the instruction. It might be in the disk drive, right? It might generate PTE miss. It finally moves copies the page table entry, page into main memory, and copy page table entry into the ITLB, and it can access again. Okay? Then what it generates? It should generate page miss because you just copied page table entry, but you don't have actual instruction page. So you have to move instruction page from disk drive to main memory, and then you re-execute the instruction, and then you have a TLB hit, and also page hit. You can do the translation, and you generate cache miss, right? Because the instructions are in main memory, but not in the cache. So cache miss, you fetch a block into this cache, and then you fetch the instruction, you decode, and so on. Okay? Okay, so this is homework. Next Tuesday. Okay? Okay, let's go to virtual memory a little bit more detail. Sometimes a computer system may not have virtual memory. They might have physical memory only. And early supercomputers, they didn't support virtual memory. So most of these cray machines, old PCs, and some small embedded systems, they only support physical memory. And the programming will be quite difficult because you have to think about physical memory size, and there is no copying in on demand. So you have to move this secondary storage to physical memory by yourself. Okay? So the address generated by the processor is actually a physical address. They generate physical address directly, go into the main memory. A system with virtual memory, the operating system maintains this page table. Okay? So CPU generates virtual address. You look up page table through the TLB. If you hit, you can find physical address and you can access the main memory. Okay? And since every time you access memory, you need this translation, and if it's done by the help of operating system, it's too slow. So the hardware accelerate this translation through TLB or MMU. Okay? So in the exam, I can say MMU, then you should know MMU is same as TLB. Okay? Page fault. Sometimes you do the translation, but it turns out that that address is not in main memory, in the disk drive. Okay? And then this is called page fault. Page fault, operating system is involved, and they should move this page from disk drive into this page frame. Okay? And correct this page table entry. Next time you access, you can access main memory directly. Okay? This is called page fault, page or page miss. And how do you solve this page fault? Okay? So first, processor signals the I/O controller, and it generates, I want to read a block of this size starting at this disk address, and copy this block into main memory at address Y. Okay? So, and then the disk controller actually has this mechanism called direct memory access. Direct memory access means without CPU intervention, it can copy block from disk drive to main memory by itself. Okay? Without DMA, actually, plus every byte has to be moved into CPU register and copied into main memory, which actually occupies important CPU cycle. It's waste of CPU cycles. It's slow operation. So actually, processor can ask the I/O device to the DMA. Okay? And then DMA, under the control of I/O controller, they know the start address of memory and start of disk drive, address of disk drive. They know the size. And internally, they have a counter size. Every time they transfer bytes and they decrement or increment counter, and as soon as the counter becomes the length, then they complete. And then the I/O controller interrupts the processor. Okay? I/O is complete. And then on an interrupt, CPU actually handle. So some process is waiting for I/O. It means in the operating system it's in the blocked mode. So process can be in different states. Okay, we will study from the operating system. So it can be run, which means the currently is assigned CPU and it's learning the instruction from this process. It's run. Okay, it can ready. Ready means it's ready to run, but there are maybe other process. So there is a queue, FIFO queue, and it's waiting in the queue. And some processes are blocked, which means it's not ready yet. It's waiting for I/O. Okay. Whenever the I/O is completed, the interrupt controller interrupt the processor, and processor go into the kernel, and the operating system change the state of this process from locked state to ready state, and move this process into the tail of this queue. And then when it becomes the head of the ready queue, it can be assigned the processor and can be executed. Okay? And then a suspended process somehow resumed, and it can run again. Okay? So memory management means physical memory is shared by multiple process, concurrent process. Okay? And each process is partially redundant. And somehow, if you have two process, virtual address 10,000 here, virtual address 10,000 here, they are totally different address, right? It might reference some instruction. For this process, it might reference some data, right? If the program is much smaller. Okay? So, how we resolve this conflict? And what if two processors access something at the same address? Okay? What can you do? And we already know the answer. For each process, we have separate program address space, virtual address space. So they can see only their program address space. They cannot see other virtual address space. They only see virtual address space. Okay? So it's inherently protected. Even if you try to access, you cannot see other space. You only try to access. The problem is some of the regions are shared, right? Some, such as printf, which is the common kernel routine, right? Then it's shared means it's mapped to different virtual address, but they are mapping to the same physical address, and it should be protected somehow. Okay? And that's also protected in some way. So in general, by providing a separate virtual address space for each process, we can do the protection, because no longer how strong you are, you cannot see other codes or other data, because you can see only your codes and data. Okay? So in this example, you have two virtual address space, which means two process, and some virtual pages are mapped to physical page frames, and some of them are shared, and this might be read-only library code that can be shared. Okay. Protection and page table. For each page, we actually put extra information to protect more, which can be access information. So for here, this is readable, writable. So for this virtual page is readable, yes, but not writable, which means this is read-only page. Okay? So for this page, if you're trying to do a write, image access violation. This page is readable and writable. This might be a global variable that can be written multiple times. And this is maybe non-readable, non-writable, or whatever. This is, and so on. Let's look at the advanced translation example a little bit more. So we have virtual address, we have physical address. Virtual address can be divided into virtual page number and page offset, right? And to access the tag TLB, you need to generate TLB index and tag. TLB can be fully associative or set associative or direct map. So fully associative, this virtual page number, entire virtual page number becomes the tag. But if it's direct map or set associative, this should be break down into tag and index portion. Okay? After you do the translation, you generate physical address. From the physical address, you can divide physical address into tag, index, and offset, or physical page number and page offset. Okay? Let's look at the example. So assume some simple memory system. 14-bit virtual address. 한효정, what is the program size for this machine? what is the maximum program size? Hmm? 16 kilobyte. Right? Exactly. Huh? 16 kilobyte. That's right. Pyeongchang, what is the maximum DRAM size? 4 kilobyte. Okay? And page size is 64 bytes. So which means page offset is 6 bits and remaining 8 bits are virtual page number. Clear? Okay? Okay. And physical page number is actually 6 bits because total 12 bits. Right? 6 bit page offset. Okay, let's look at this. Is assume that this is page table. Page table. So you in the page table you have 16 entries. Some of them are valid, which has this physical page frame number. Some of them are invalid. You don't have this number because it's not in main memory. Okay? You have 16 entries. Okay? And assume this kind of simple TLB. This is 16 entry, 4-way associative. Okay? So for each 4-way means you have 4 bank. Each bank you have 4 entries. Okay? Each set, how many sets do you have? You have 4 sets. And each set has 4 entries. Total 16. So you have 4 sets. So you need set in 2-bit set index and remaining bits are the tag. And this is the TLB configuration. TLB is 16 entry. Okay? Some of them are invalid, some of them are valid. For valid, you have this physical page number. Okay? And this is simple cache. Cache, you have 16 byte blocks. Each block is 4 byte block. It's direct mapped. Okay? So, direct mapped and 16 byte blocks. So, what should be the index? You need 4-bit index. Right? Byte, offset, you need 2-bit offset. And remaining bits are the tag. Okay? These are the actual data. So you have index tag and byte 0, byte 1, byte 2, byte 3, and so on. Okay? Let's do this. Example 1. Using the same example, for this virtual address, find out TLB tag, TLB index, and find out all this using the previous slides. And generate the physical address and find out index tag and offset and hidwire miss and so on. Right now, okay? And if you are brave, you can come to this front and you can give us a right answer. I give you 5 bonus points. Any volunteer? 5 bonus points. 5가 너무 작나? Example. Okay. So this is binary, right? This is hexadecimal. So this is 1, 2, 3, 4, 8 bits virtual page number. This is 6-bit page offset. Among virtual page number, this 2-bit is index, and this is the tag. Okay? And you have to look up TLB first. Where's the TLB? TLB index is said 3. Okay? Index is 3. That's right. 3. And tag is said 7. It's valid. But tag is here is another 3. Right? So tag mismatch. Right? index 3. Okay, this is 4 associative. We have to search 1, 2, 3, 4 in parallel, right? Okay, so here this is another value. Tag is 3. So you match here. You have a hit in this bank. Okay, and physical page number is 0D. 0D. Okay, so 0D means this is translated into 0000. D means 1101 and 010100. So this is page offset. This is physical page number. Right? 맞나? Do you follow? Okay? Because the index is 1, 1, so you find index 3, and there are 4 entry. You search in parallel, and tag is 3, and tag is 3, so you have a hit, and 0D is the physical page number. So you substitute virtual page number with 0D, physical page number. From here, you generate cache, index, tag, and offset. Okay? Cache is tag is 6-bit, index 4-bit, block offset 2-bit. So this is block offset, and next 4-bit is cache index, and this is tag. Okay, so the index means 5. So index 5, this is direct mapped. So you have only here, tag is 0D. So the 0D, same, right? So you have a cache hit. And block offset is 00. So you send this byte, and the data is actually 36 in hexadecimal. Send it to the processor. Clear? 오케이, 오늘 여기까지.